Hello and welcome. My name is Partho Majumdar. In this video, we will try to understand linear regression. Before we discuss linear regression, let us look at the bigger picture of what we are trying to do in this particular course. Now, we are basically trying to understand when and how to apply regression. Now, why do we require to do regression? Say for example, in my house, I want to estimate what is going to be my next month's expenses to run the family. Now, let's say for example, I've been tracking my expenses for the last 5 years on every month, and I record factors like how many members of the family have been there in the house during the month, how many festivals or birthdays we have had during the month, and what is the number of times we generally tend to go out to eat in restaurants, or what is the capital purchase we normally undertake during the month, whether it is summer or winter, whether the electricity bills are going to be high because of AC usage, etc. All these parameters I'm tracking. Now, I have this data with me. Based on this data, I say that next month I'm going to have, let's say, 5 members in the family. Then let's say there are 3 festivals and there are 2 birthdays in the coming month, and other factors which I've been tracking. I give an estimate value for all of that. Based on that, I want my model to tell me what is the amount of expense what I'm likely to have in the coming month. So such problems can be solved using regression. There are a number of applications of regression in industrial usage also. Say for example, I'm running a cigarette factory. I want to estimate what should be the amount of raw tobacco I should purchase so that my factory production level for the coming month is up to what it is expected to be. So there will be various factors based on which the production will vary, and based on those factors I want to estimate, based on the historical data what I have, how much amount of tobacco I should get from the farmers so that my factory can run seamlessly without any stoppage. So such problems we can solve using regression. One form of regression is linear regression. So in this particular video, we will try to understand what is linear regression, and then we will try to extrapolate this idea to other forms of regression. Let us start our discussion with a very simple problem. Let us say that we have just two variables, x and y. So I have got a variable x and I have got a variable y. Say for example further that x variable is actually the age of a person and the y variable is the weight. So I have the x variable as x and I have the y variable as weight. Now I have been tracking the values, like for example, if the age is 45, the weight is 70. Like this, I have been tracking data for many people over a large sample. I have this data with me for different age, what is the weight that has been observed. Based on this observations that I have got, I want to be able to predict, supposing the age is 51, what is likely weight this person is going to be having. I want to be able to estimate that. So this is my problem. So we have two variables here, x and y, and based on the value of x, I want to predict the value of y. So my x is the independent variable. This is the independent variable. And y is the dependent variable because y depends on x. So I have my independent variable x and my dependent variable y. So based on the value of the independent variable x, I want to predict the value of the dependent variable y. So what we could do is that when we have all this data with us regarding the x and y, I can plot this on a graph. So I can put on one axis my x and on one axis I can put my y. So I can make a graph now. So on this graph I can plot the different ages on x-axis as our example states, and on the y-axis I can plot the different weights. say for example, I have plotted that for this particular age, the weight is here, or for there's another value which falls here, there's another value which falls here, and I plot this is according to the random sample what I have got. I have taken many people's weights and ages, and I'm making a graph out of that. So I have these data with points with me, based on which I want to make a prediction for y for a given value of x. Now, when we have a data like this is basically a scatter chart between x and y. Now, what I can do is that I can try to draw a line. I can try to draw a line such that that line represents the value of y for a given value of x. Supposing I draw a line like this, now I want to make sure that this line is a good prediction based on the value of x if I have to predict the value of y. But how do I know that this is the line which actually will give me the best estimate? I could have another line also here which could have been another possibility for predicting the value of y for a given x. Now, let's say for example, we find out that this is the line. How do we find out? Let's discuss that. What we do is that, supposing we take any of these lines, let's say this is the line which I have taken, which seems to me that this is going to be the best estimate. Now, on this line, what I do is that I see the predicted value of x, that is here, and I see the actual value of x, that is here. So for this particular value of x, the actual value was here, whereas the predicted value is here. Now, the difference between the actual value and the predicted value, this is the error in my estimate. So this much is the error in my estimate. So similarly, if you take this point, now there is this distance here, this is the predicted value and this is the actual value. So this is the error in my calculation. If I take any other point, so from this point, this is the actual value and this is the predicted value. So there is a difference between the actual value and the predicted value, and the difference is the error. Now if I take all the errors, and if you notice that some errors are positive, some errors are negative. So it may happen that the negative and the positive may null out each other. So for that, what I do is that I take the error and I square it. If I square it, all the errors become positive, and then once I square it, I sum up all the errors. So I will make a sum of all the errors, and this will give me the sum of errors. If I divide the sum of errors by the number of observations that I have, I get the mean square error. So this becomes the mean square error, because this is the mean of all the errors squared. Now this squared error which I have got, squared mean square error which I have got, this is basically in square terms in comparison to the value which I have been using. That is, the value of x and y are in units, and this is in square. So if I make a square root of this becomes the root mean square error. Now the root mean square error will be in the same units as the observations. So now I have got a value which is the root mean square error. Now what I do is that I take all the different lines which I have tried to draw, and I see the line which has the least amount of root mean square error. The line which has the least amount of root mean square error can possibly be the line which will give me the best prediction for the value of y for a given value of x. So this is the way, if I am able to find this line will become the line of my linear regression, so that using this line I can predict the value of y for a given value of x. Now we know that equation of a line is y is equal to mx plus c. Now here c is a constant, x is the variable, the independent variable, and its coefficient is m, and y is the dependent variable which we are trying to predict. Now this is the equation of any given line. Now in this line, if you notice that, supposing I make x is equal to 0. If I make x is equal to 0, so if x is equal to 0, then y is equal to c. So this line, if I let's say this is my line of the linear regression, and when I make x is equal to 0, that is x is here, and so y becomes equal to this value, which is but nothing but c. This value c is what we know as the intercept. So this is the value known as the intercept. So intercept is the value of y when x is equal to 0. Also notice that in this line, when we increase x by 1 unit, the increase in y is given by m. So this m is known as the slope of the line. So for every unit increase in x, y will increase by the amount of slope. Now these are the essential terms which we need to find out in order to do our linear regression. Now what we have done is that we have created a linear regression equation where we have only one independent variable and there is one dependent variable. However, in real life, we will have the dependent variable y depending on many independent variables. Let's say we have got independent variable x1, x2, x3, etc. So we have right now we have taken 3 independent variables. Now for this we can draw a linear regression equation where we can say that y is equal to beta 0, which is the intercept, plus beta 1 is the slope of x1. So beta 1 is the unit by which y will increase given x1 and x2 and x3 are constant and x1 is increased by 1 unit. So plus beta 2 x2 plus beta 3 x3. Now for every linear regression equation, we will always have a small term which is known as the error term. We normally represent it by epsilon. So this becomes my equation of the linear regression. So if I am able to get this equation, then I can put in the values of x1, x2, x3, and I can expect to get a value of y. So the problem in linear regression is that for a given set of variables, that is x1, x2, x3 up to xn, I need to find these betas, the beta 0, beta 1, beta 2, beta 3, etc. so that I have an equation based on which, giving the values of the independent variables x1, x2, x3, I am able to get the value of the dependent variable y. Now let us extrapolate the idea that we have just discussed. Supposing we have again a simple case where we have just 2 variables x and y, and we have plotted x and y for different observations that we have made. So supposing this is my plot. Last time what we did was that we tried to figure out a straight line between these points which gives us the estimate. Now supposing I try to figure out a curve which goes through like this, and this curve is going to give me the prediction for a value of y given a value of x. Now this kind of a curve can be obtained by a polynomial. So supposing I have a polynomial, then I can obtain a curve like this. Now supposing this polynomial is of degree 2, it becomes a quadratic equation. So it becomes a quadratic equation, supposing it's of degree 2. So if I'm able to figure out, instead of a straight line, if I figure out a equation of degree 2, I get a quadratic regression. If I am able to figure out a line of a higher degree, then it becomes a polynomial regression. So I can extrapolate this idea of linear regression to higher forms of regression, which can be obtained by using higher degree equations.